Let's talk briefly about the integral test as a test for convergence, and then I think it's really cool to see how it turns into a bound on the remainder. When you are looking at an infinite sum, ideally you're going to figure out exactly what the whole infinite sum is, but unless the series is very, very special, like the geometric series, it's probably going to be impossible to get a closed formula for that. They're just not that nice. And so instead, you're going to look at a finite sum, and then you'd like to have some idea of how close you are to the idealized limit, the infinite sum. So just briefly, very much like what's in most books, like Stewart, for example, if you've got a sum, an infinite sum of terms, a sub n, um, and let's say these are all non-negative. So it's all about I'm adding up a bunch of numbers, positive numbers, and do they get small fast enough so that the sum converges? And we're not getting into this yet, getting into the situation where the reason they converge might be a lot of nice cancellations between numbers that otherwise aren't super small. So we're looking at this kind of sum, and we're in the situation where suppose that we have a formula, let's say y equals f of x, some function of a real variable that gives those numbers when you put in integers. And so it's an extension of that, the sequence of numbers to all real numbers. And then we can say, well, you know what? One thing that seems somewhat similar is taking the improper integral 1 to infinity of f of x. And so that would be the area under the curve, starting here and going off to infinity. And of course, that has its own issues of limits and definition, but there's a lot of wonderful tools. Ooh, forgot the dx, my bad. There's a lot of wonderful tools, basically the fundamental theorem of calculus, antiderivatives, that kind of thing, that let us sometimes get an answer for whether this converges and sometimes gets an exact answer for what the actual interval is. So how does that compare? These aren't the same notion, but there's a really nice geometric comparison. So first of all, what I do is I look at this sum and think this is kind of, compare it to a really low-tech, low accuracy rectangle method for this improper integral, which is with delta x equals 1. That's just rectangles of width 1 put under this guy. And there's a little bit of an offset issue, which is going to be actually very important for the error estimate. Let's say I do a right endpoint method for now. And so that means if I take f of 1, that's equal to a sub 1. That's the height of this guy, and the width is 1. So the area of this is exactly a1. Here, I make sure that I evaluate the function f of 2. That's the same as a of 2. And then I put the rectangle off to the left. That's a2. Then this is a3. Then this is a4, a5. And here's the cool thing. The area under those rectangles is exactly going to be this summation. And I'm playing a little fast and loose with the limit ideas, but it really does work. And that's clearly, well, let's see, it's not quite less than this area under here, but it's less than this area plus just a finite number a1. So in this case, what we're getting is that if this area, the integral, is finite, then the area under the rectangles is going to be finite. It's something less than that plus this finite number a1. That's great. So that's the main first thing, is that if the integral converges, so does the sum. Very cool. Now, you might think, okay, that's all that's going to happen. With this picture, for example, with this exact picture, I wouldn't ever be able to prove that the sum of the a's is bad, because this looks like a comparison that it's always going to be better than something here. And if I know that this integral diverges, the area under the whole curve, well then I'm less than that. So how can I say anything definitive? It's better than bad. Well, the clever thing you can do is, hey, whoever heard that the right endpoint method is the only rectangle method that exists? What about the left endpoint method? It's natural to try it. So that's going to be where I take the number a1 and I make this rectangle. And I take the number a2 and I make this rectangle. a3 is this rectangle. And suddenly, oh my gosh, we're going to have something where now the a1 plus a2 plus a3 plus a4 is bigger than the integral. And so if this guy diverges, so does sum a spin. Okay. Okay. So one thing to note is that you might worry that this picture is maybe a little bit simplistic. In particular, that this integral, this function is everywhere decreasing. And so that's something we do have to make sure. To make this really technically correct, this guy had better be a decreasing function. If there's a lot of wiggles, this could get subtle. Okay. And of course it has to have an integral and all that kind of stuff. Okay. Or at least it has to be continuous so that there's no issues with the integral right in the middle. So, but this is, as long as f of n is a decreasing function, then this is really literally true. And so we have a convergence and divergence test. This is great. This is very powerful when it works. The problem is it's a big deal to assume that the formula for the function it can be extended to a function of a real variable that we know how to integrate, and then you know whether this converges. That's not a trivial thing. So let me start the example I want to talk about in this context. This will probably be a two-parter, but because when we get to like the integral remainder. So for example, something moderately complicated. I'm going to go from 2. You'll see why in a minute. This never really matters. This can be 1, 2, 1,000, a million. As long as it's a finite number, in terms of convergence, it never matters. Okay. So I'm going to look at 1 over n. That would be the harmonic series. And then I'm going to soup it up a little bit on the bottom with a cube of the log of n. Now, this one famously diverges, and the integral test can be used to show that, although there's simpler ways. But I'm making it a bit better. Now, log n is not very big when n is large. Cubing it definitely helps. So it's not exactly clear if that's enough help to make these guys go to 0 fast enough for it to converge. And this is exactly where the integral test is really helpful. When it's not obvious, when these guys don't get to, say, like an exponential level of increase in the denominator, which would be a exponential decrease for the whole thing, which would be like a geometric series, and there you don't need such sophisticated tests. But let's see. Does this converge? And we're also going to say, can we find an estimate for the actual sum by maybe taking a finite sum of the terms and then getting some sort of bound on what's left over, the remainder or the error. Okay, so this one's pretty straightforward to apply the integral test to. Here, f of x, when I just write it as a function of x, it's just using a different letter. But of course, it's a big conceptual jump. That the idea that I know how to systematically put real variables into here. This is decreasing. I'm not creating some function that has some wild oscillation that's going to complicate things and make the integral test invalid. That's very rare that that's an issue with these kinds of simple examples, but it could be. You want to make sure that that's going to happen. And it's decreasing simply because once n is past 2, this guy's increasing, so the whole thing is decreasing. Oh, and of course I put in n equals 2 to start. The reason I couldn't put n equals 1 is that log of 1 is 0, and this wouldn't make any sense at that point. Okay, so that's a decreasing, and it's continuous as long as I stay at 2 and above. Okay, and so I'm going to look at the integral from 2 to infinity of dx over x log cubed of x. Okay, that's cool. U equals log x. Yay. Du equals 1 over x. Yay. Dx. Okay, so this is just du. And so this is the integral. Okay, and then let's see. It's a definite integral, so let's be real careful about this. If x equals 2, u is log 2. And this may not be quite sufficient level of rigor for the AP. This is how people really would do it. As x goes to infinity, to figure out what the other upper limit does, as x goes to infinity, that means u will also go to infinity. Because when you put in numbers go big, 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 then the logs are going to be big as well. So this turns into log 2 to infinity. And it's just du, that's the dx over x, over u cubed. Yay. Okay. And that's going to be minus 1 over 2, 1 over u cubed, from log 2 to infinity. And the main thing is that this is going to converge. When u goes off to infinity, let's at this stage, let me go ahead and make sure there's really a limit going on here. This is minus 1/2 t to the t cubed, and then minus a minus, so plus 1/2, and then log cubed. Sorry, log squared. Ooh, that's a square. My bad. Log squared 2. And here's the key thing, is that as t goes to infinity, this goes to 0. It does converge. So this is finite. And so this converges, and so I can say that this guy converges. This is better than something that's good. Now, this number here is not particularly relevant. It's not the sum of this guy, because remember the picture we had, there was some real gaps underneath these things. Those gaps really are meaningful. And so I can't say this is the sum, or even that this is a particularly good estimate for the sum. But what we're going to do next video is we're going to take this like from n to infinity. And this number is going to be very useful in terms of helping us figure out error bounds and getting a pretty darn good estimate for the sum. But this is an example of how you would carefully evaluate an improper integral, or pretty carefully evaluate an improper integral, show that since it is convergent, then the corresponding sum is convergent, and that you would say by the integral test.